Hey everyone, Chapter 6 is going to be our first chapter that goes into the reactions of a specific functional group. So in Chapter 6 we're going to focus on the reactions of alkenes. We saw a little introduction to this in Chapter 5, but then we kind of veered off and talked about general reaction energies. In this case, in this chapter, we're going to go through and we're going to look at 7 different reactions, each of them following the same general strategy or outcome, but each one will have some small differences. This first video for Chapter 6 was going to be a little bit long because this is going to set up our knowledge to build on that as we go into the subsequent videos. Alright, so let's start out by looking at just the generic reaction. I'm going to give you a little overview of where we're going before I then dive into the addition of hydrogen halides to alkenes. This is a reaction I showed you already, but there's going to be a lot more details that we're going to dig into and learn about. So, like we saw before, the general reaction of these alkenes, the general type of reaction, is going to typically involve the reaction of the pi bond of the alkene with some group. I just have it here, Y and Z. Oftentimes this Y and Z will be a polarized bond where we have a delta plus on one side and a delta plus on the other, but we'll see that's not always true. So often what happens is that the pi bond reacts with the delta plus end of this YZ molecule, breaking the bond between the Y and the Z. Alright, this is going to lead to the formation of an intermediate where that Y group is attached to one end of where the double bond used to be, leaving a carbocation on the other end. So we saw this already, right? This is a carbocation intermediate. Alright, once that carbocation forms, then the reaction can complete by the attraction of the carbocation by the Z minus group that's generated in that first step up above. Alright, so minus and plus are attracted to each other like we saw before, and by doing this we end up with Y attached to one end and Z attached to the other end. So this is an addition reaction. Right? All we're doing is adding those groups, and specifically it's called an electrophilic addition reaction. And that is because that first step involves the pi bond reacting with an electrophile. Alright, so in all the reactions that we're going to look at in this chapter, they're going to follow this same pathway. So we're going to add a Y and a Z across the pi bond to form this kind of product. And the only difference between all the reactions okay, is just the identities of Y and Z. Alright, let's say the identities. Alright, so let's look at an overview now. Reaction is going to be. So here's a table For all of them, the reactant is just an alkene shown here. And we'll see sometimes it depends on what's attached to those bonds that are attached to the alkene. But for this first introduction, it doesn't really matter. All right, so let's look at what we've got here. So in the first reaction in the upper left, X here is going to be a halogen. This is what we saw before, HBr adding across the double bond. This is sometimes called a hydrohalogenation. Hydrohalogenation. All right. The next one, notice now instead of HX, we have H on one side and we have OH on the other side. So we add H to one side and OH to the other side of the double bond. Okay. In this case, notice we're just starting with water. Right? We're adding water to a double bond, so it's just like adding water to ourselves, right? What do we do when we, drink some water? We're hydrating, right? So this is a hydration reaction. All right, we can do a similar reaction down here. We've got now H and OR, so remember that R is an alkyl group. So now we're reacting the alkene with an alcohol, but the same type of reaction takes place, right? We still add an H to one side, and we add the oxygen to the other side. This time the oxygen is just carrying another alkyl group along with it. All right, so in that top one, when we did the hydration reaction, our product was an alcohol. When we do this next one, when we add an alcohol, our product is an ether. All right, the next reaction is adding two halogens. Right, so this is just a halogenation. Right, so we just get an X on each side where the double bond was. Upper right, we're adding two H's, so this is a hydrogenation. Okay, in this case we're going from an alkene to an alkane. So we're saturating the molecule, right? We're starting with an unsaturation and we're getting a saturated product. In the next one, this isn't really a reagent, but we're just going to add oxygen across the double bond. So this forms an interesting three-membered ring with an oxygen in it. This is called an epoxide. So this is an epoxidation. And these epoxides have some interesting reactivities. In the next reaction, this one's really interesting. So we're going to start with O3 here. Anybody know? Do you know what the name of this is? Okay, so this is ozone, right? It's found up in the atmosphere. And when ozone adds to an alkene, it forms this cool ring. Right here, this is called an ozonide. But when we do a second reaction to this, and it ends up splitting the original double bond right down the middle, and it puts an oxygen on each side. Right? So we generate two carbonyl compounds. And it breaks the carbon-carbon double bond. This is called an ozonolysis. Right? Lysis, right, means to break. So I'm going to break a bond using ozone. All right, so we're going to start out up here looking at the hydrohalogenation. We've kind of seen this reaction already, but there's some details that we'll have to go into. All right, so here's just a couple of examples. All right, so I'm just going to start out here by adding this to HBr. All right, sometimes it helps when we have a double bond like this in the beginning, especially to go ahead and draw in the missing hydrogens that we don't really need in our skeletal structure, but just so we don't forget that they're there. Alright, so in the first step of this reaction, the pi bond is going to react with the delta plus end of HBr, right? This is plus, this is minus, because bromine is more electronegative than hydrogen. So the pi bond reacts with the H, and the electrons between the H and the bromine go onto the bromine. Alright, so what kind of a reaction is this? Alright, so this is just really just a simple acid-base reaction. Right? Or the pi bond could be the nucleophile, and the H would be the electrophile. That's why it's called an electrophilic addition. Alright, so if we do this, we're going to create an intermediate. Alright, so we're going to draw this. The H could go to either side of that double bond. I'm going to draw it to the left side just because that's going to make it easier to draw. So the new H is there, and we form our intermediate. So we form our carbocation intermediate. And then the second step of this reaction involves the bromide that we generated in that first step. Remember, bromide has 4 pairs of non-bonding electrons, and this minus, this anion, is going to react with the cation. And so now we've got our product. We've added H to one side and a bromine to the other side. Alright, so this reaction works as long as X can equal either chlorine, bromine, or iodine. Okay, fluoride doesn't really work so well. Okay, so let's just look at another example here. We don't have to draw out all the intermediates and the whole mechanism this time. We're just going to add to this cyclopentene. We're going to add HCl this time. Okay, and to draw the product, all we have to do is draw the same carbon skeleton. Let's do like we did last time and put the H's in here. Okay, so we're going to get an H. Here's the 2 original H's. And we're going to add the H from HCl to one side, chlorine to the other side. Okay, simple addition, electrophilic addition reaction. Alright, what about this next one? Okay, so we only have one H here that we can fill in with. And we're going to add HBr. Right, but when this reaction takes place, we have a choice. Before, because those molecules were symmetrical, there was only one possibility. It didn't matter if the H went on to either end of the double bonds, but this time it does matter. Alright, so let's see, which one should we put it on? We can put the H on the top carbon first. So that means, here I'll draw this H. So that's the methyl group, remember. And we can add the H here. That would leave a plus at that position. So we'd get this carbocation, secondary carbocation. The other possibility is that we add that H to the bottom position, like this, and so we get this carbocation here. Now, the reaction going to one or the other is going to give us a different product, right? So let's finish this mechanism. So here we have bromide. Of course, it's going to go to the position that has the carbocation. All right, so In this case, we put our H at the top position and our bromine goes here. And for the second reaction, the second intermediate, the bromine goes to the other position. And we get this product. Alright, so what's the difference between these two products? Right? How are they related? Okay, how are these related? Okay, they both have the same formula, right? But they're different. They have a different order of connectivity. So these are constitutional isomers. Alright, so do we think that one of them will get formed more or less than the other? It turns out that these are not formed in equal amounts. And it's this bottom one that is the major product. Okay, so let's see if we can understand why that is. All right, so it's going to depend upon the energy pathways, right? So whichever of these carbocations gets formed faster, that the product that comes from that carbocation is going to be the major product. So it tells us here that this carbocation right here must be favored. Okay, so let's look at something about the stability of carbocations. All right, so carbocations in general, let's just say in general, cations are usually stabilized by electron donating groups. Okay, because a cation is short of electrons, it makes it more stable if there's something else that can donate some electron density to it. Alright, so in this case what we're looking at is different amounts of substitution around the carbocation. Okay, so we could start with just H's all around here. This would be the methyl carbocation. Remember what we said about these cations before, in that they are sp2 hybridized, making them trigonal planar. So they have a p orbital on them, empty p orbital. We could draw that up here. I'm going to draw this kind of from the side, so I'm going to use a wedge and a dashed line. So we're looking along the plane, and we're going to have this empty p orbital. Alright, so at one end we have the methyl carbocation. Then we could add one alkyl group and have two H's. This one we would call a primary carbocation because the cation, the carbon bearing the plus, is attached to one carbon. Okay, the next one, we put two alkyl groups. Alright, this would be secondary. And the third possibility is if we have three alkyl groups, this would be a tertiary carbocation. Alright, now alkyl groups, though they're not great electron donors, can donate some electrons into that pi bond. So down here on the lower, well, on the lower right is the methyl cation that I drew up above, even though it was down here. But remember that this is empty, right? An empty p orbital. So next to that, we have these sigma orbitals, all right? That's made up by these sp2 hybridized orbitals on carbon, and this sigma bond can donate some electron density into that empty p orbital. All right, this is a process or situation called hyperconjugation. All right, this can only happen if we have sigma bonds on the atoms adjacent to the carbocation. So if we have a methyl carbocation, like up here, right, there's no sigma bonds up here that can line up with the p orbital, so this has no hyperconjugation. We had one alkyl group, that can have some hyperconjugation. If we have two, both of them can have hyperconjugation. If we have three, all three of those. So the more alkyl groups that are attached to the carbocation, the more stable that cation becomes. Okay, so as we go from left to right, this becomes more stable. All right, so the more stable carbocation is going to be the preferred one that's formed during the first step of this reaction. So let's look at the energy pathways leading to these two intermediates, the two carbocation intermediates that I showed you on the last slide. So in both of these, they're going to start at the same point, right? So we have a reactant here. Right, we had another reactant, right, which was HBr, right? And that HBr reacts with the alkene to form two possible carbocations, right? We have, these are the two that we showed before. We have a, let's see, what would the classification be here? So if we look at this one, here's the carbocation. This carbon is attached to two different carbons. So this is a secondary carbocation. The bottom one has three carbons, right? 1, 2, 3 attached to the carbocation. So this is a tertiary carbocation. We just learned that the more substitution around the carbocation, the more stable it is, right? So that tertiary carbocation is more stable than the secondary carbocation, right? And we know that this one proceeds to its reaction. It's going to give us a bromine here, and if this one proceeds, it would get this constitutional isomer. All right, so we know the relative stabilities of the carbocations, but just because a carbocation is more stable, does that tell us that it necessarily affects the rate, right? So is it the stability of the product of this step that affects the rate, or is it something else? So you remember, right? So rates, what are rates controlled by? Okay, by the activation energy, right? The energy of activation, right? And so that's going to be how big of a hump that the molecules have to get over in order to get to these intermediates, right? So just by showing the products doesn't tell us how fast they're formed. All right, so there's a way to understand this, and in fact there is a relationship. All right, so in this diagram there are three different lines, three different reaction coordinate diagrams. Okay, on one, in blue, we start up here at a higher energy and we form a product that's lower energy, right? So if this is free energy, this is an exergonic step. Right? If we look at the green one, it starts down low and finishes up high, and so this is an endergonic reaction step, and the one that's red starts at one energy, finishes at the same energy. So delta G would be 0 in that case. All right, so there's a rule, or it's called a postulate, the Hammond postulate, that tells us how we can relate the reaction profile, the thermodynamics, to the kinetics, to the rate of the reaction. So the Hammond postulate says that the transition state is more similar in structure to the species reactant or product that is more similar to it in energy. All right, so let's look at the transition states. So here's a transition state here, 1, and if we compared it either to the reactant or the product in this reaction step, the structure of that transition state is going to be more similar to the reactant because that's what it's closest to in energy. All right, if we look at the reaction in green, then we have, here's the transition state, and it's going to be more similar in structure to the product of this because the product is more closer to it in energy. All right, so what we can say is that for an exergonic step, okay, the reactant or the transition state is going to look more like the reactant. In an endergonic step, the reactant or the transition state, the structure of the transition state is going to look more like the product. So an important aspect of this is that we have a hard time understanding or knowing or predicting the energies of, or the structures of the transition states in other ways, because remember that these transition states are on an energy maxima, right? So they're on the top of a peak, and we can never isolate and really probe those structures. They don't exist for very long, right? So this Hammond postulate helps us predict something about the properties of the transition state based upon either the reactant or the product using the Hammond postulate. Okay, so let's take this back to what we were doing in this reaction. Okay, so we already talked about this. We go from our reactant to our two products. So the Hammond postulate tells us that because this is an endergonic step, that the products of this step will be more similar, the transition state leading to them will be more similar to the products. Okay, so let's draw these in. What that tells us is that the transition state is going to be stabilized by whatever stabilizes this product. So let's just draw out what we think the transition states would look like. Okay, so let's do it for the lower energy one. So remember, the transition state is where we're breaking and forming the bonds. Okay, so in the transition state going to that tertiary carbocation, we're going to be breaking the pi bond, so we're going to put a dashed line for a partial bond. We're going to be forming a bond to the H. We're going to be breaking the bond to the Br. Okay? So the other part of this is in the process we're going to be forming a plus charge at the tertiary position, so it's only partially formed at this point, and the bromide is taking those electrons with it. Okay, so this is a transition state that would go right here because we're forming that at the tertiary position. All right, the other possibility is that we are adding the H to the upper position. So again, we'd be breaking the pi bond, we'd be forming a bond to the H at this position. Let's just draw in this H over here. we'd be building up delta plus over here and a delta minus on the bromine. So let's look at these two transition states and see if we can predict which one would be more stable. Alright, so what I would say is, because we know a more substituted carbocation is more stable, we should think that a more substituted delta plus is also more stable. Alright, so the energies of the transition states kind of mirror the energies of the products here. So the other transition state would be somewhere up here in energy and go like this. So this would be the transition state here. So the only reason why we can imply relative stabilities here, because secondary here is going to be similar to the secondary transition state up there, is because of the Hammond postulate. Okay? Alright, so the other part of this is, or this is actually another rule that will allow us to predict the outcomes. Alright, so let's follow through this step. Okay, so again, the pi bond will attack the proton, and the electrons will go over to the chloride. All right, this is going to form two possible carbocations. Right, we could add the H to the end. It would form a carbocation here, a secondary carbocation. If we add the H to the middle carbon, or the interior one, then we're going to get a plus out here, and we'd have a primary carbocation. Right? And then chloride could react with these, and we get a chlorine here, or chlorine over here. Alright, so what did we learn from the Hammond postulate? Which of these two routes would be more favored? Alright, we can say that secondary is more stable, and because this is an endergonic step, the transition state leading to that will also be more stable. Alright, so this is going to be more stable, it's going to be formed faster, and it's going to lead to this product over here as the major product. Okay? Alright, so in this rule, Markovnikov's rule, what it says is that the electrophile, so that's H here, okay, adds to the carbon, right, there's a carbon of the double bond that has more H's, all right, and the nucleophile adds to the carbon with fewer H's. Okay, so this is Markovnikov's rule. The other way that I would say it is that the H goes to, I'm going to call this the less substituted side, because that has less carbons attached, and this side is going to be the more substituted. Alright, so the H is going to go to the less substituted side, leading to the more stable carbocation, and the X group, the halogen will go to that more the more substituted carbon. Okay, so H goes to less substituted. Cl or X could be bromine. We'll see it in other ones. Let's say X goes to the more substituted. Carbon that has more carbons attached, fewer hydrogens attached. All right, and the main reason that this is true is because it's going through the more stable carbocation. All right, so one other thing about this. Okay, so in this reaction, we have two possible constitutional isomers as products. Okay, and in this case, one of them, the one on the left, is going to be formed in a greater amount. Okay, we have two possible. One is formed in greater amount. Okay, so it's selecting for one product over the other. And it's selecting so the chlorine ends up in one region of the molecule, here, rather than over here. So we call this a regioselective reaction. Okay, so a regioselective reaction is one that has the possibility of forming more than one constitutional isomer, but it forms one or some of them more than others. All right, so let's just play this out a little bit. Let's just do some more examples. All right, so we're adding HCl to this alkene in the upper one. All right, so we're just going to add an H to one side. We're going to add a chlorine to the other side. All right, so we want to know if it has one product or if it can form more than one. All right, so we could add the H to one side, chlorine to the other side, but in this case, because it's equally substituted, we could have the H here and the chlorine over there. So in this case, we're going to get two possible products, probably in roughly equal amounts. Okay, so we're going to get a mixture of these two. Right? Of course, we're adding an H in this process too, but in these skeletal structures, you don't have to always add that H, right? All right, what about the next one? We're adding HBr, right? We're going to add the H to the less substituted end, so that's going to go out here. The bromine's going to go to the more substituted end. Right, so we're going to get a structure that looks like this. We're going to have a CH3 out here and a bromine here. So this is following the Markovnikov's rule. All right, what about the next one? We're adding HI, right? The H is going to go to the less substituted side here. This position here just has one carbon and one H, right? This position here has two carbons, so the H goes to the less substituted side. The iodide goes to the more substituted side because that's where the carbocation will form. Right, so the iodide will end up at this position. Okay, what about the bottom one? One more example. All right, so how many products are we going to get here? We're going to get a mixture. Okay, we could add the bromine to this end, the H to the other end, or we could add the bromine to this end. Right? So do we get two products? No, these are actually the same, right? Because if we name these 1, 2, 3, 4, 5, 6 is 3-bromohexane. On the other one, of course, we'd number from this side. 1, 2, 3, 4, 5, 6. 3-bromohexane. Right? So it's because this one is symmetrical. There's the same, an ethyl group on each end. We get the same product. Okay, so we can also do this in kind of a reverse direction. So let's look at a product, a haloalkane, and predict what alkene could be used to form that. All right, so the key thing is here is that the double bond has to be attached to the position where the chlorine is. Okay, so we have really two possibilities. We could put the double bond here, right? Or we could put the double bond going the other way over here. All right, so if our goal was to carry out this reaction and get the highest possible yield, would one of these be better than the other? All right, well, this one would be better, right? Because if the chlorine goes on this side, it gives us 3-chlorohexane. If it goes on this side, we get 3-chlorohexane. So we only get one product out of this one. But if we do the reaction with this alkene, we can have the chlorine at the 2 position or the 3 position. So we're going to get a mixture. So we want to pick the alkene that would give the best yield. All right, what about this bottom one? Okay, so we got our bromine at that highly substituted position. Right, so we can work backwards. Remember, the double bond has to go to this position. So we could either have the double bond going up to that direction, or we could have it going to the left, or we could have it going to the right. All right, so how many of these do we have? Okay, these two are the same. All right, so we actually have 2 possible alkenes that we could start with that would work well for this reaction. All right, so both of these would give that product if they follow Markovnikov rule. So the H would go to the less substituted side, bromine to the more substituted. Or the H goes to the less substituted, bromine goes to the more substituted. Okay, so either of those would be just fine alkenes, precursors, reactants. Okay, so let's do another one. All right, let's draw this out. This is going to react just like all the other ones have. H is going to get protonated, or the alkene is going to get protonated. All right, so what do we think we should get? Okay, let's draw this out. We've got our carbon skeleton, and we predict the bromine to go here, right? Because the H goes to the less substituted side, we would expect the bromine to go to the more substituted side. All right, but I'm going to throw a little monkey wrench in here, because I'm going to say, no, this is not the product that gets formed. And in fact, look at this. This is the product that gets formed. Whoa, this is the major product. So how could that form, right? Doesn't make sense. So one way we can try to figure this out is that we can start either from the beginning or we can start from the end, and we'll try to link it together in the middle. All right, so let's follow what we drew for our arrows up there. Let's draw the intermediate. Okay, so if we do that, put an H out on the end, and we get this secondary carbocation. Okay, let's work backwards from the product. All right, so we should know that the bromide has to react with the carbocation. Right, so this tells us that we have to have a carbocation at that position. So the question is, how do we get from one carbocation to the other? All right, we got to shift that carbocation over one position. So can we just do this? Can we just like move that over to the next position? Well, no, we don't really move cations, and that one can't hold a cation right now anyway because it has an H there, right? It's all has its complete octet. It's not going to have a plus on there. So what we have to do is draw our arrows in the reverse direction. So what happens is we have this H here. That H can bump over to the adjacent position, taking those electrons with it. All right, so what's moving is H with 2 electrons. All right, so an H with 2 electrons is going to have a minus charge. Anybody remember? Do you remember what this is called? Okay, this is called a hydride. Okay, so this we call a 1,2 hydride shift. Okay, the 1 and 2 just means that those positions, the H is going to jump to the next carbon over. Okay, this just means that they're adjacent positions. It doesn't have to be the 1 and the 2, like if we were naming this position 1 and position 2. It just means the H is going to bump over to the next carbon over. All right, so why would it do that? Okay, so it's going from a secondary position. What's it forming? Okay, it's forming a tertiary carbocation, right? So we know that the tertiary carbocation is more stable. All right, so just like we know that with Markovnikov addition, H goes to the less substituted side so we can form the more stable carbocation, but if we can do a hydride shift to form an even more stable carbocation, then that will take place. All right, then bromide just reacts with whatever was the most stable carbocation. All right, so it's getting kind of tricky here. All right, let's look at some other examples. All right, so in this case, pi bond reacts with the H and we lose chloride, just like always. Okay, we form a secondary carbocation, right? So do you think the chloride is just going to react with that? Okay, we don't have any H's over here, right? These are all CH3s, but even a CH3 can move. So if this CH3 brings its electrons with it, then we move that methyl group there, and the plus goes to the point where the methyl group came from. Okay, so remember this had an H here already, so now that position has 2 methyl groups and an H. So we've gone again from a secondary carbocation to a tertiary carbocation. Then chloride can react with that tertiary carbocation, so we get this rearranged product. All right, so our chlorine is at this position over here. This one's not a hydride shift, but this is called a 1,2 alkyl shift. Okay, so it shifted a methyl group, so it would be a methyl shift, but you could have other alkyl groups that could shift as well. All right? And the reason, remember, is that we're being able to form a more stable carbocation. All right, let's try one more. Okay, we start the same. That's a plus here, right? But in this case, if we get a 1,2 hydride shift, it doesn't make it any more stable. It still goes to secondary. So this one has no shift. And we would just get the chlorine at this position. All right, so what we're really looking for is when we have a carbocation with a more substituted position adjacent to it. That's when we'll see either hydride or alkyl shifts. So we want to look for a carbocation next to a more substituted position. Okay, that's where we'll see the shifts taking place. All right, let's do one more. We just can't get enough of this stuff. They always start the same, right? Always start the same. Okay, so we have a plus like this. What do you think is going to happen now? Okay, one possibility, bromide just reacts with that. Like this. Okay, what's another possibility? Okay, we see that we have a carbocation with a more highly substituted position next to it. So one thing that could happen is we could get a 1,2 hydride shift. And if we did that, we'd end up with our plus at this position. The H would move over to where the carbocation is, taking the electrons with it, leaving this position short of electrons now. All right, and so then bromide could react with that carbocation, would give us this product. All right, that's kind of what we've been seeing. What if I said there was one more possibility? Okay, I'm going to draw it back over here. What if I said that we could get this product? Dang, look at that. It's not even the same ring size. That's crazy. All right, so what we can have, even though this is in a ring, what if one of these groups, instead of the H, what if this carbon-carbon bond jumped over here? So this would be an alkyl shift. All right, if we did that, okay, here's how I would draw it sometimes. Okay, if I can fit all this in. Okay, so what I'd like to do sometimes is just take this bond, right, it was right here, and I'm just going to move it over to the next position. All right, so this is going to go over to here. Okay, and it's going to leave behind a plus. Okay, it looks like I added something extra in here. Let's check it out. Okay, that's going to leave, where's the plus going to be? So the plus was over here. This bond moved over there, moved away from there, so the plus would be right there. Okay, and so then the bromide, we could redraw this. Sometimes this helps if we draw it crazy like that, but then we redraw it. And so then we count how many carbons we have. Let's start with the carbocation. We have 1, 2, 3, 4, 5, 6. So now we're going to have 6. We're going to have the methyl group here. We're going to have a plus over here. All right, is that the most stable that we can get? No, it's not even. All right, so what else can happen? So now this can even do another 1,2 hydride shift. All right, to form another carbocation. This is getting crazy. I can barely fit this in here. So then we move that over there. We get a plus here. And so what I'm going to have to do, I can't erase that. I'm going to X this dude out. Sorry about that. And the bromide is going to go where that plus is. Okay, so we have 3 possible products. One is just our direct electrophilic addition reaction, no rearrangements. 2, we had a 1,2 hydride shift. Right? This is a 1,2 hydride shift pathway. Gives us that product. And why would that pathway want to take place? Because we're going from secondary to tertiary. The carbocation is becoming more stable. All right, the third possible product is this one over here. All right, so why would this take place? All right, it's going from, let's look at the substitution of the cations. Secondary to what did we get when we did that alkyl shift? We just got another secondary. So why would that be favored? Okay, the reason it's favored, even though the cation has the same substitution, is because we've gone from a 5-membered ring to a 6-membered ring. And a 6-membered ring is more stable. Okay, so this has a cyclohexane. Okay, here. And this is more stable. All right, so then we went to that secondary carbocation here. That's the same one. But if we did a 1,2 hydride shift, we got to the tertiary carbocation here. And then we've gotten just as stable as we can get. All right? So this is a complicated one, huh? All right. So this is the end of video 1. So what have we figured out here? Okay, we've looked at and we've learned how to predict the products when we add hydrogen halides to alkenes. Right? We know something about their carbocation intermediates. We know that the major products are going to be formed via the most stable, most substituted carbocations. All right? We can propose mechanisms for those. Remember, the mechanisms involve showing arrows like this, which mean the movement of electron pairs to show the reactants and products and the intermediates. All right? And we know how to predict the relative stabilities of those. The other thing we've learned about is we've learned about hydride and alkyl shifts. All right, so in the next video, we'll go on and we'll look at the addition of water. So this will be the hydration reaction. It's going to follow exactly the same process that we've just looked at for the addition of HX.